Now, after understanding all these three processes of solid to liquid, liquid to gas, gas to solid, gas to liquid, we go ahead with what is known as latent heat of a substance. What exactly is this latent heat and how does it play a role over here? When we talk of latent heat, we say that latent heat is nothing but it is the stored amount of hidden energy in a substance, which is responsible for change of physical state. Just to elaborate on this, or just to explain how latent heat concept works out, let's consider a crucible which is filled with, say, water. I am supplying it heat in order to, say, prepare tea or whatever. I'm just heating it from bottom when it's placed on a tripod stand. What is happening to the water inside? You see, slowly and steadily the heat is being transferred to the water that is inside, such that the temperature of water is increasing from room temperature towards 100. It hasn't reached 100 as yet. It takes some time to reach the state of 100 degrees C. Yes, now it is slowly approaching 100 degrees C. See what is happening now. As it is approaching 100 degrees C, the rise in temperature is gradually decreasing. Look at it now. What is happening? Now we see that the temperature is remaining constant. This temperature is called as boiling point of a liquid. But then we are still providing it with heat. So where is that heat going? This heat that we are supplying across is getting stored inside the water as a hidden form of energy, which is not being shown by the calibration in the thermometer. As a result, the temperature reading is constant. So this stored amount of energy is being utilized in converting water into steam. So we see slowly and steadily that the vapors are being generated and this water is getting converted into its gaseous state. That means this hidden form of energy which was stored inside water on reaching 100 degrees C is responsible for the change in physical state. And since this is happening, we say that this particular energy that is stored is called as latent heat of a substance. This latent heat of substance is utilizing it in converting the liquid state into the gaseous state, hence called as latent heat of vaporization of steam. A similar process we can talk about as far as ice into water also is concerned. We see that ice starts melting and slowly and steadily gets converted into water. It isn't an abrupt process. It takes certain amount of time wherein this ice is getting converted into the liquid state. So we see that this ice that is getting converted into the liquid state is utilizing certain amount of heat energy which is hidden inside the ice. This hidden form of energy is called as latent heat of fusion of ice or melting of ice. So two types of latent heats we are going to study: latent heat of vaporization of steam and latent heat of fusion of ice. With this, we have understood what is latent heat, we have understood what is the heat content, we have understood what is principle of calorimetry. There is one small thing which we have as a day-to-day example, wherein there is a phenomena that we apply which is called as the phenomena of regeneration. When we apply the phenomena of regeneration, what exactly is regeneration? Let's consider a huge ice slab that is being placed across two supports. We are applying force on the ice slab. When we try to apply a force across a ice slab with the help of two weights that are attached to a nylon string, we see that where the nylon string is in contact with the ice, it is melting. That means ice melts when a force is being applied on it. On application of force, the physical state is getting converted from its solid state into its liquid state. That means ice melts. As a result, the string starts moving downwards. As the string starts moving downwards, we see that the layer of ice that is above the string now is devoid of any external force. Since it is devoid of any external force, this ice is recombining or reuniting or refreezing together to give you back the slab of ice. So this phenomena of reunion of ice after the external pressure has been released is called as regelation. So how do we define regelation? When an external force is applied on a slab of ice, it melts. On release of this external pressure, the melted ice refreezes back or reunites back to give you again the slab of ice. This phenomena is called as regelation. We have an application of this when we go across a skating ground. We see that when the skater moves around a skating ground, he, with the help of his skates, creates grooves across the field or the ice field that is there. How is it that these grooves do not remain still as they are after they have been prepared by the skates? The phenomena is same. When an external pressure is applied, definitely it is melting ice, therefore the groove is being made. But when he has already passed through that particular surface of ice, we see that this particular ice is reuniting back or refreezing back because of the sub-zero temperature environment that has been provided, and this later on works as regelation. So with the phenomena of regelation, we definitely know that ice reunites, refreezes back to give you back its solid state. We have a concept of freezing mixture also. What exactly is freezing mixture? Freezing mixture is nothing but a mixture of ice and salt in the ratio 3:1, wherein salt is added to ice so as to bring down its temperature. The temperature that is brought about is sub-zero temperature. So what is the use of a freezing mixture? I don't know whether you have really seen these kulfi walas, the ice candies that are there. Now these kulfi walas are going to carry the kulfi in a solid state, in a frozen state, all throughout, say, your chapati. How is it that they can maintain the solid state of ice or kulfi? It is purely on account of the freezing mixture that is surrounded across the kulfi. In this case, we see that sprinkled salt across ice surface is being covering the kulfi all throughout. It isn't that he is carrying a refrigerator, a mobile refrigerator all throughout. He has this particular physical phenomena which is occurring, which definitely is enabling him to provide the kulfi in a solid state. And this freezing mixture remains intact so long as he wishes to, because he just has to sprinkle salt, common salt, across the ice to maintain these temperatures. So we see that heat and calorimetry do play a vital role in our day-to-day life. There are plenty of examples as far as specific heat capacity is concerned, latent heat is concerned, and so on. Just to quote a few over here, we must have seen that when we go in for long drives, very long drives, say something like you're driving from US to Canada, and then you're going through the large distances of say 1000 kilometers or 1500 kilometers, we see that the engine of the car becomes hot. Why? Because the car radiator becomes hot. The heat transfer is taking place. The fuel is being burned and the engine becomes hot. Now at that particular juncture where the engine becomes hot, what do? Yes, we definitely pour water in the car radiator. Now what is the function of water that is poured in the car radiator? It definitely absorbs that amount of heat that is making the engine hot. As a result, the cooling effect is very fast. And why does water do it? Because water has the highest specific heat capacity. With this property of water having largest specific heat capacity, it definitely cools the car radiator, thereby enabling it to perform further. So car radiators can be cooled by just pouring water into it. Another very good example, when you normally play cricket or football or badminton, you normally tend to sprain your hand or get a twisted arm or so. In that case, we do apply some sprays or painkillers and so on. But add on to it, we use fermentation bags. Have you seen a fermentation bag? Fermentation bag is a bag which is made of rubber, and you put in hot water into it. Now this fermentation bag you're going to apply wherever you're going to have the sprain. What happens because of that? The heat that is stored inside the water is being transmitted to your body, thereby relieving the pain that is there in your body. So definitely fermentation bag is used as a painkiller because of the property of highest specific heat capacity of water. Another example of water having high specific heat capacity can be given as in cold countries wherein you have severe winters. The ice slam that is there across the ground is almost there for almost 3 months, 4 months, and it is difficult to store fresh vegetables and fruits. In that case, what we do is that we keep the fruits as well as vegetables inside water. So we store them inside water purely because water has a capacity to inborn capacity to store its specific heat capacity. So this specific heat capacity that is present in water enables the fruits as well as vegetables to remain fresh even in severe cold countries wherein you have snow almost 6 months a year. So this also gives you a very good example for water having high specific heat capacity. Then we go on to steam also, wherein we say that steam burns are more severe as compared to water. Why are steam burns more severe as compared to water? Because the latent heat that is being stored inside steam, that is approximately 2268 joule per kg, is very high as compared to that of water. So steam burns are much more severe than that of water, and so on. So basically you have large number of applications as far as water is concerned, steam is concerned, ice is concerned. We will be seeing those application based questions henceforth. So we are moving on to theory application based questions. Let's consider the first one. What is the relation between a joule and calorie and joule and kilocalorie? As I said, these are both units of heat. So we have to find out the correlation between joule and calorie and joule and kilocalorie. We have a straight relation because that's a mechanical equivalent of heat, a calorie. 1 calorie is equal to 4.2 joule. 1 calorie is equal to 4.2 joule. Remember, when you're writing the word joule, it should always be with a small j. If you're writing the symbol j, it should be a capital J. And as far as joule and kilocalorie is concerned, 1 kilocalorie is equal to 4200 joule. 1 kilocalorie is equal to 4200 joule. Most of the time they do give you these values in the examination, but one should remember it also. Luck by chance, if you feel that you are not given the value, so you should know these values of conversion between calorie to joule and kilocalorie to joule also. Let's consider this question. What are the practical consequences of high specific heat capacity of water? Another way to say, what is the use of water having high specific heat capacity? We have already mentioned those, but still I'll repeat it over here. Due to high specific heat capacity of water, we have fermentation as one of the basic application, wherein we see that hot water is used in bags so as to relieve us of pain. Second one is as coolants in car radiator, wherein car absorbs the heat, thereby cooling the car engine. Then prevents freezing of bottled wines. That also is one very good example, because then you can keep wine bottles into the water container so that it is preventing the content of wine to be frozen. Land breeze and sea breeze is also a very good example of high specific heat capacity of water. So when we see that land breeze is blowing or the sea breeze is blowing, we see because of the high specific heat capacity, it is maintaining the balance of temperatures across both the sea and the land. How about this question? We had studied this part in your change of physical state, wherein we talked about three processes wherein liquid is getting converted into the gaseous state. They are asking you what are the differences between boiling and evaporation. Just two processes they are asking. So we have one in case of boiling, that it takes place at a fixed temperature, which is called as boiling temperature. Evaporation takes place at all temperatures above room temperature. Boiling is a rapid process, is a fast process. The rate at which water gets converted into gaseous state is faster as compared to evaporation. Evaporation is definitely a slower process. Boiling takes place throughout the volume of the liquid. So this phenomenon of boiling is throughout the volume of liquid, but evaporation is a surface phenomena. So it takes place only at the surface of the liquid. And of course the last one, as I said, boiling. In case of boiling, the vapor pressure equals atmospheric pressure. In case of evaporation, vapor pressure is less than atmospheric pressure. And since vapor pressure is less than atmospheric pressure, it is slow to get converted into the gaseous state. Let's pick up another one. Explain how following factors affect the rate of evaporation of a liquid. The temperature of the liquid. Greater the temperature of liquid, more is the rate of evaporation. Area of exposed surface. Supposing I have a small crucible in which I have liquid, and if I have a huge plate and I have to spread the same liquid across the plate, we see that this particular extended surface or extended exposed surface area is going to give you a faster rate of evaporation. Third one, moisture in the surrounding air. So when there is moisture in the surrounding air, the temperature of the air outside or in the surrounding is going to be less. So less amount of heat will be supplied to the liquid that is to be evaporated. So definitely the rate of evaporation will be much lesser in a moist climate as compared to a dry climate. So all these three factors we have studied. Of course, there is one more factor, what we say as the wind. When you apply wind on for evaporation, the rate of evaporation is faster. You must have seen in rural areas, you must have gone to certain rural places wherein there is no proper transport facility also. If you go in such rural places and you see people sipping a cup of tea, what happens is that they do not sip the tea directly from the cup. They pour it into a saucer. Why is it poured into a saucer? Not because they like it or they enjoy it. It is because it is increasing the surface area. At the same time, while drinking, they are going to blow wind across it, so that the wind is going to cause the cooling effect. Evaporation always causes cooling effect, and hence the blowing of wind will definitely help cooling of the tea faster. Next question is what I said just now. Why does evaporation produce cooling? Again, this is because the latent heat is required to convert the liquid into the vapor state and thereby extracting heat from the content of the liquid. So this latent heat that is utilized over here is basically used to remove the heat that is present in the liquid by blowing air through it. So we say evaporation produces cooling. Let's consider another one, in which case it is stating which one of the two. It's a comparison now. Methylated spirit. Methylated spirit is nothing but a volatile substance. So which one of the two, methylated spirit or water, has a higher boiling point? Higher boiling point meaning thereby the temperature at which it boils is higher. It's obvious. I mean, the answer is so obvious that water definitely will have a higher boiling point, purely because methylated spirit is a volatile substance. Even kept at room temperature, it is going to evaporate. Relate your answer to the different cooling effects that are produced by two liquids at room temperature when spilled on the hand. So I'm going to spill methylated spirit on one hand, I'm going to spill water on the other hand, and then I'm going to compare the boiling points with respect to the evaporation that is taking place. I know evaporation is going to produce a cooling effect, and evaporation will only occur when it has attained its boiling point. So let's consider that these two substances, methylated spirit and water, are placed on hand. And now I am trying to find out which of the two is going to cool up faster. It's obvious, as I said, methylated spirit being a volatile substance is going to volatilize, get converted into the gaseous state. Thereby this hand is going to be proven to be having a cooling effect much faster than this particular hand. This will take some time, maybe a day also, because I'm not supplying it with any external heat but the body heat that is there from the palm. However, this one, the heat that is present in the body is enough to volatilize it. As a result, we say that this one would give a better cooling effect, and the boiling point of this is methylated spirit is less than that for water. Another one, which one of the two has latent heat? Water at 0 degrees or ice at 0 degrees? Remember, latent heat is correlating with the substance that is getting changed or forming another physical state. So it is ice that is melting into water, and hence the latent heat will be present in ice rather than water. So ice at 0 degrees C has the latent heat. As a result, it melts.